Hello APC Mechanics students, in Unit 5 Rotation, Class 11 5.3 Rotational Dynamics Part 3. Section 1 Rolling Without Slipping Interpretation. In the previous class we have seen explicitly how to determine the expression of the linear speed and the acceleration of the center of mass of a rolling object without slipping. In contrast with pure translational motion, the result can be summarized as then translation versus combined motion, pure translation rolling without slipping. Now the system and the variable of motion. We are talking about the system, which is a falling object on a smooth ramp inclined by theta. We know that the speed at the end of the ramp would be given by radical to gh, and a is given by g sine theta. Now if you modify our system and it becomes an object rolling without slipping on a ramp inclined by theta, v would be modified by a factor, as we said previously, which is given by 1 plus ICM over mr square, as well as the acceleration. So what is the interpretation? Variables of motion for rolling without slipping can be determined from pure translational motion by compensating for a fractional term given by 1 plus ICM over mr square. So v in this case would be updated into radical to gh divided by the fractional term. Similarly for the acceleration. As the object is more inertial, the fractional term, which is given by 1 plus ICM over mr square, increases, then both the acceleration and the velocity decrease in value. Now here, let's investigate the following table. So in the first row we have the object that we will discuss, rotational inertia, velocity, and acceleration. So we're gonna handle the following objects. Now these 1, 2, 3, 4, they perform combined motion rolling without slipping. As for the cube, it's pure translational motion. So for the first row, the rotational inertia is not applicable, which is basically 0. The velocity at the end of the ramp is given by radical to gh, and the acceleration is given by g sine theta. For the solid cylinder, it's similar for a disk. Now the rotational inertia is given by half mr square. Now plugging, so if we're talking about the velocity, if we plug this term here and we perform the calculation, so what do we have? We have 2 over 1 plus half, which is basically 2 over 3 over 2, and that would be given by, now 2 over 3 multiplied by 2gh, or let me say 2 over 3 multiplied by 2. Then here I didn't multiply by 2, I kept 2 over 3 in order to indicate the factor that have been changed. Now similarly for the hoop we can do the following. Now for the hoop it's given by mr square. So if you calculate the fractional term, that would be, for example, 2 over 1 plus mr square divided by mr square, they cancel. That would be 2 over 2, which is basically half multiplied by 2. For this reason here we have the following factor half and we have the factor half. Similarly for the solid sphere you can do the calculation, and for the hollow sphere. And here let me characterize the following objects according to the values of the acceleration and the velocity. We notice that in the case of the cube, where it performs a pure translational motion, the velocity and the acceleration, they are greatest in value, so this is ranked as 1. Now after that we have the 0.71 for the solid sphere, so this is ranked as 2. Now after that we have the solid cylinder, which would be ranked as 3. Now we have the hollow sphere, which is ranked as 4, and that would be 5. So what does this mean? That the cube has the highest acceleration and velocity. Here we're talking the velocity at the end of the ramp. Then in the second place we have the solid sphere, in the third place we have the solid cylinder, and then we have the hollow sphere, and the most inertial one is the hoop. Now if you perform this experiment, so here at the end of the ramp, what do we have? So initially we have objects that are released from rest. So basically this is the cube, and that's the solid cylinder. This is the solid sphere. This is the hollow sphere. This is the hollow sphere, and that would be the ring. Now that would be the cube. That would be the solid cylinder, and In the third place, we have the solid sphere. Then we have the hollow sphere. Then we have the ring, which is the hoop. So the hoop is basically the ring. So as we can see that the calculation indeed agrees with our experiment. And here let me mention something very important. What is the difference between a hollow sphere and a solid sphere? A hollow sphere in which the mass is only distributed along the radius of the sphere, whereas a solid sphere, the mass is distributed among the sphere. So basically you can do the analogy between the disk and the hoop. Now, section 2, acceleration of a freely rotating rod. A uniform rod of mass capital M, length L, and moment of inertia ICM is pivoted from one end. The rod is released from rest from the horizontal position. The aim of this section is to determine the speed of the bottom of the rod when it passes through the vertical. So basically we have the following rod of length L and mass M pivoted at this point. We're gonna release the rod from rest. The rod is allowed to rotate around this pivot point. We are interested in determining the speed of the rod as it passes through the vertical position, but the speed of which point? The speed of the bottom of the rod, as has been mentioned in the text. So the speed of the bottom of the rod. This problem can be solved using Newton's second law or conservation of energy. However, in order to proceed with the Newton's second law, we require to understand what is meant by simple harmonic motion that will be induced in Unit 6. For that, the problem will be solved using conservation of energy. We assume that frictional forces are negligible. Since there is no friction, then the mechanical energy is conserved. Now, before we start, we need to take the P level to be the horizontal plane passing through the center of mass of the rod when it is in the vertical position. Here, since the rod is of uniform mass distribution, then the center of mass is located at the geometric center, which is basically here. Then we're gonna choose the P level to be the horizontal plane, the horizontal level passing through the center of mass. So that's our P level. And now we're gonna apply the conservation of energy. Energy initial is equal to energy final. Kinetic plus gravitational is equal to kinetic plus gravitational initial and final. Because it's released from rest, that would be 0. And at the vertical position here, in which we wish to determine the speed of the bottom of the rod, we're gonna assume that the center of mass passes through the P level, so that would be 0. And that would be given by mgl over 2. Now here, we suppose we have h. What does h represent? H represents the distance between the center of mass from the initial position to the final position. Now initially the rod was situated here. So that would be the height, or basically let me repeat myself and say, what does h represent? H represents the distance from the center of mass initially to the P level. So initially our rod was situated something like that, and the center of mass is located here. If we're assuming that the rod is of length L, then initially the center of mass, if we choose the P level to be here, the center of mass is located at a height h, which represents the half of the length of the rod. For this reason, h has been replaced by L over 2. Now mgl equals to I omega square. Here we have done the cancellation effect for the factor half. Now omega can be related to v if you're interested in determining v by okay, before I say so, let me apply the parallel axis theorem. Why here we're applying the parallel axis theorem? Because the moment of inertia I here represents the moment of inertia about this pivot point, because the rod is rotating around this pivot point. And we know that the moment of inertia of the rod about its center of mass is given by ICM. Now ICM can be related to the I around this pivot using the parallel axis theorem. And it's given by ICM plus md square, in which d represents the distance from the center of mass to the pivot point. So if this is the pivot point and this is the center of mass, the separation distance would be L over 2. For this reason, we have added a counter term given by m multiplied by L over 2 to the power of 2. So that would be ml square over 4. And we know that omega can be related to v by v over L. Now why specifically L? Pay attention, this is very important. Here we're interested in determining the speed of the bottom of the rod. And in general, omega is given by v over r, where r represents the distance from the point that we're interested in calculating the speed to the axis of rotation or the pivot point. In this case, because we are interested in determining the speed at this point and our pivot point is this point, so the distance represents this the length of the rod, which is capital L. For this reason, it's given by v divided by L. Now replacing omega by v over L, we would have v square over L square. And here, the way to proceed with this expression is to place ICM in the form of ICM divided by mr square or ml square. For this reason, I will divide here by ml square divided by ml square. No need here to divide by ml square because we already divided on the left hand side and they are multiplied by each other. This would cancel with this L, and we're left only with one L, so we would have the following, and this cancels with this, and we would have 1 over 4, and we're left with the following expression. Now, moreover, here we can simplify one of the L's with the power of 2, and we take L to the upper side. That we would have GL is equal to the following. And now we're ready to isolate for v square, which is given by GL divided by 1 over 4 plus ICM over ml square, which means that v is the radical of the following expression. Then the speed of the bottom of the rod when it passes through the vertical is given by radical GL over 1 over 4 plus ICM over ml square. Now you can think about the following. Since we have the speed, one can think of determining the acceleration of the rod, but here it doesn't work. Why? Because the type of motion is not uniform accelerated motion. While the rod is falling down from the initial position to the final position, what's causing this rotation actually is the torque produced by the pull of gravity on the center of mass as it falls down. And such type of motion is dictated by simple harmonic motion in which the acceleration is proportional to the displacement and not constant. In brief, what I'm trying to say is that while the rod is falling and it's gonna pass through the vertical position, the acceleration is not constant, it's changing. So in brief, the acceleration is varying. So we cannot use kinematics because kinematics are based on the fact that the acceleration is constant. The way to proceed with that is using calculus, as we shall see in Unit 6. And now we're gonna solve the following problem as a direct application on what we have explained. A uniform rod of mass m and length L is attached to a pivot of negligible friction as shown above. The pivot is located, so this should be a pivot. At a distance L over 3 from the end of the rod, express all answers in terms of the given quantities and fundamental constants. What are the given quantities? Capital M and capital M. Capital L. So now whenever we determine an expression, we need to double check that it's being expressed in terms of N and capital M. In part A, we need to calculate the rotational inertia of the rod about the pivot. Now we know that the rotational inertia of a rod about its center is given by 1 over 12 ml square. The first thing to notice that this expression is not given in the exercise itself. 1. 2. If it is given, we need to apply the parallel axis theorem in order to determine the new rotational inertia about this pivot point, which has been shifted from the center. But because the rotational inertia about the center, which is 1 over 12 ml square, is not given, and we know that it's not required from us to memorize the rotational inertias of different bodies, we can solve for part A using integration. Then let me say, since the rotational inertia of the rod is not given, then we cannot apply the parallel axis theorem to deduce the rotational inertia around the given point. However, we can always use integration, which is given by the integral of r squared dm. Now, in order to calculate this integral, the first step that you should do is choose the origin to be the axis of rotation or the pivot point itself, and setting our boundaries we got. So we're gonna choose the origin to be the pivot itself, and we're integrating from the left end of the rod to the right end of the rod. Now remember that this is an oriented axis. Any position given to the left would be negative, any position given to the right would be positive. Now if it's located at a distance L over 3 from the left edge of the rod, so that would be minus L over 3, and that would be 2L over 3. And in this case, our boundaries of integration would be given by follows. And notice that here we have two variables given by R and L. They are the same because these are meters, but the two variables that we're talking about is distance and mass. And the unification between the variables can be done by referring to the mass distribution. Now we need to unify our variables, and as we said, this can be done by referring to the mass distribution. Since the rod is of uniform mass distribution, then we have the following identity. Differential mass over differential distance would be equal to the total mass over the total length. And we're now here, either we can set the integral completely depending on mass or depending on distance, but because these are fixed, it is easier to change mass into distance, and this is done by isolating dm. Then dm is given by capital M over capital L multiplied by dr, and now we can replace it in the integral. Now m over L, this is a constant, can be dragged out, and we're left with the following unified integral in one variable. L, R, and R, all of them agree because they are in distance. What is the integral of r squared? That would be r cubed over 3. From 2 over 3 L to minus 1 over 3. So we need to compute this once at this minus once at this. We can factor out 1 over 3. So 1 over 3 has been factored out, and we're computing r cubed once at 2 over 3L and once at minus 1 over 3L, and we consider the difference. Now here, because the power is odd, so we have an additional minus sign with minus that would give us plus. So power cube would be for all of this fraction, which give us 8 over 27, and similarly here that would give us 9 over 27, and if we do the simplification, we're left with 1 over 9 ml square. So what does this quantity represent? This is the rotational inertia of the rod around the pivot point. Now remember that the unit of inertia is given by kilogram meter square, and indeed we have kilogram meter square, which is a dimensional analysis check on our answer. Notice that this result could have been obtained if the moment of inertia of the rod around the center is given. Let me do the following. So we know that I, the center of mass of the rod around the center, is given by 1 over 12 ml square. Now if I apply the parallel axis theorem, that would be 1 over 12 ml square plus the term which compensates for the shifting, that would be the mass, multiplied. So if this is L over 3, then what about this distance? If this as a whole is given by L over 2, so the separation distance from the pivot to the center of mass is given by L over 2 minus L over 3, which is basically L over 6. So that would be L over 6 to the power of 2. That would be 1 over 12 plus 1 over 36, and as a factor ml square. Here we can do the common denominator, multiply by 3, multiply by 3. That would be 3 over 36 plus 1 over 36 ml square, which is basically 4 over 36, which is give us again 1 over 9 ml square, which is the same result that we have obtained here. Now, so far we know that the rotational inertia about this pivot is given by 1 over 9 ml square. Why this is important? Because now anything that we need to calculate, whether rotation around this pivot or the torque, we need to use the following rotational inertia. In part B, they're asking us to, so they're saying the rod is then released from rest from the horizontal position shown above. Calculate the linear speed of the bottom end of the rod when the rod passes through the vertical. And as we know that, because we didn't yet investigate unit 6, which is the simple harmonic motion, this can be determined using conservation of energy. The speed of the bottom of the rod when passing through the vertical position can be determined by the conservation of energy, since frictional forces are negligible as been stated here. So now, before we start, we need to identify the P level, the horizontal level passing through the center of mass when the rod is in the vertical position. This is the vertical position, and that would be the center of mass. So let's define our P level to be the horizontal level passing through the center of mass. And now we can apply the conservation of energy. Energy initial is equal to energy final. Ki plus UGI is equal to Kf plus UGF. Now initially we don't have any kinetic or speed, that would be 0 plus mgh, which is equal to half I omega square plus 0. Now here, why we don't have translational speed? Because we're assuming that the rod is performing pure rotation and there is no translation. Now what does h represent? H represent the initial distance of the center of mass to the PE level. Initially, before the rod reaches the vertical position, we assume that the rod, because it's rotating around the pivot, it has the following position. And the center of mass is located somewhere here. Now that would be the distance h. If all of that is L over 2 and this distance is L over 3, so we're interested in h. H in this case would be L over 2 minus L over 3, which is basically L over 6. So for this reason, h would be given by L over 2 minus L over 3, because remember that initially the rod was given in the following position before it rotates and reaches the vertical position. So initially the center of mass here, from the PE level, h is given by L over 2 minus L over 3. So, and here in this case, omega would be replaced by V over R, and we know that the moment of inertia around this pivot point is given by 1 over 9 ml square. Now, here there is something tricky we should pay attention about, let me mention, but first let me say that 1 over 2 minus 1 over 3 is 1 over 6. And here we have replaced the moment of inertia by 1 over 9 ml square, and here we have V square over R square. Now what does R represent in this case? R represents the distance from the point that we're interested in determining the speed to the pivot. Remember that we're interested in determining the speed at the end of the rod, which is here, and the pivot is given in this case to be this point. If the distance over the rod is given by L and this part is given by L over 3, then the distance from the pivot to the bottom end of the rod is given by 2L over 3. So in this case, R will be replaced by 2 over 3L. Now here, okay, so that would be 4 over 9, because it is in the denominator, it will flip and becomes 9 over 4. So 4 and 9, which is downstairs, becomes upstairs, and 4 remains here. Now here we can apply the cancellation effects for the masses for L square and for 9 as well, and we're left with the GL over 6 is equal to half V square 1 over 4. So that would give us V square is 4 over 3 GLY, because 2 multiplied by 4 would give us 8. If we take 8 to the other side, that would be 8 over 6, which is basically 4 over 3. Then in this case, the speed of the bottom of the rod when it passes through the vertical position is given by the square root GL. Now why this is reasonable? Because G has the unit of meter per second square and L has the unit of meter, then that would be meter square per second square, and it would be for perform the radical, that would be meter per second. And now for the rest of the video, we're gonna solve the following exercises. A sphere starts from rest at the top of a ramp as shown above. It rolls without slipping down the ramp. The potential energy of the sphere Earth system is 0 at the bottom of the ramp. Which of the following is true when it reaches the bottom of the ramp? So here the energy is completely gravitational and here it's completely kinetic, but we know that because it's performing rolling without slipping, we have two types of kinetic energy given by half mv square plus half I omega square, which means that if at this point, the bottom of the ramp, the gravitational potential energy vanishes, it means that all of this energy has been converted into translational and kinetic energy. For this reason, the sum of its translational kinetic energy and rotational kinetic energy equals to the initial potential energy of the sphere Earth system, which is D. And here remember, even so rolling without slipping, we have friction, but there is no dissipation of energy because friction doesn't perform work. Exercise 2. In an experiment, students roll several hoops down the same inclined plane. Each hoop has the same mass but a different radii. Each hoop rolls down the incline without slipping. Which of the following graphs best shows the linear speed v of the hoop at the bottom of the incline as function of the radius r of the hoop? Now we know that the moment of inertia of a hoop is given by mr square, and sorry, let me make this more clear. So the moment of inertia of a hoop is given by I, which is mr square. So if you're interested in calculating then it's given by mr square, and we know that the speed at the bottom of the ramp for a hoop is given by the radical of 2gh with a fractional term given by 1 plus ICM, yes, over mr square, and we know that ICM in this case is given by mr square, so this cancels with that, and we're left with radical 2gh over 1 plus 1, which is basically radical gh. Now as you can see that whether the mass or the radius changes for a hoop, the result would be the same, independent whether the radius of the hoop is small or large. As r varies, the speed at the end of the ramp would be the same. For this reason, A would be the correct answer. The result, the speed is constant as function of r. Now exercise 3, a sphere of mass m and radius r and rotational inertia I is released from rest at the top of an inclined plane of height h as shown above. If the plane has friction so that the sphere rolls without slipping, what is the speed of the center of mass at the bottom of the incline? And we know that it's given by the following expression, radical 2gh divided by 1 plus I, which is I around the center of mass, divided by mr square. Now notice that none of the answers conform with this because we need to do some modification. Now here we can do the common denominator, so that would be 2gh over mr square plus I over mr square. Here we can do the common denominator and we can take mr square out, up, so that would be the radical of 2gh mr square divided by I plus mr square, which makes E to be the correct answer. Now exercise 4, a solid sphere, a hollow sphere, and a ring all have the same mass and radius. Each is released from rest at the top of the same incline and rolls without slipping down the incline. Which of the following indicates the object that will reach the bottom of the incline first and provides correct reasoning? We know that the one that will reach the bottom of the incline first, that have the highest acceleration and the highest linear speed, which is the less inertial body. Now we know that the hoop, so the ring has the highest, so that would be the greatest. So let me say that this is 3. So this is the most inertial one. We know that the mass distribution, which is the solid, this is the less inertial, and in the second place comes the hollow sphere. Then the correct answer would be E, the solid sphere, because it has the smallest rotational inertia. Now exercise 5, which is the last exercise for today's video. Two discs have equal masses and radii. Disc A is solid and disc B is hollow, so we know that now A is less inertial than B. Each disc has a thin string wrapped around it. Both strings are attached to the ceiling as shown. The discs are simultaneously released from rest from the same height. Which of the following accurately describes which disc will hit the ground first? We know that A will hit first because it is less inertial. So we're gonna choose either A or B, but we need to choose the correct reasoning. So sorry, it should be either A or C. So disc A will hit the ground first because disc A has smaller rotational inertia, therefore it will have greater linear acceleration, making C to be the correct answer. Then that's it for me in this video, guys. See you soon in a new one.